Hello! I'm creating a new programming language called PAR. It's a very new and original language with a lot of things different about it. One thing that it does differently is concurrency. The way it does it I call automatic concurrency, and it's quite unlike anything you've seen before. Let me show you. I want to show you this concurrent program, fully written in PAR. I call it a concurrent downloader because it can download files from the internet and it can download multiple of them at the same time. Let me start it. You see, it starts as a web server, but that's just a user interface. It will display the download progress here in the console, and it accepts instructions to start downloading files via HTTP requests. And that's just so that the input and output don't interfere here. So let's see what happens when I tell it to start downloading. I want it to download this 100 megabyte file and save it as data1.dat. It immediately starts downloading, and we can see the total number of bytes to be downloaded here, and the progress can be observed here. Now let's see what happens when we add a second file. It immediately starts downloading as well, and the total number of bytes has increased. Let's add a third file. Now 3 files are downloading concurrently. And now the first file has already finished, and we can see the stats here. Let me show you one less interesting thing about this program, which is the graceful shutdown. I can press Ctrl+C and it will tell the program to stop. But it doesn't stop immediately. You see, it says shutting down, but nothing finished. That's because it waits until all of the work has been finished. However, if I would tell it to start downloading another file, it says no, because it stopped listening for connections. And now that all files have finished downloading, the program has finished as well. Now, there's nothing all that special about this application. It's just a barely non-trivial concurrent application. What's interesting is how it is done in PAR, using its automatic concurrency in a language without deadlocks, without runtime exceptions, with its whole new way to do structured concurrency. Let's take a look. Alright, so let's understand how this works and what is so special about it. I think by the end you will agree there is actually quite a lot that's special about this. Just a syntax note, the arrows are the so-called pipe operator. It's just a different way to call a function. The result of the first function gets passed into the second function, the result of that into the third function, and so on. Now the first line here, let root path equals blah blah, that just specifies the directory where we'll be saving the files. The second line is more interesting. Yield download requests. It's a function defined later in the source code. It starts the web server. It rejects all the bad requests. But for each good request, it emits a pair like this. This pair contains the URL to download from and the file name to save this to. Now the result of this yield download request function gets passed into the next function, which maps each of these pairs over the download file function, also defined later in the source code. For each of the pairs, a new download file is spawned and started. This function download file actually starts downloading from the URL and writing it into the destination file from start to finish. So it could be done here, the files get downloaded, everything is done. If we did not want to observe the progress live, which of course we do because it's boring otherwise. And that's what the remainder of the program is about. So to accomplish that, this download file function, it doesn't just download the file. While it's doing that, it keeps emitting these events. Here's the type of these events. Don't be spooked, that's just a pair. In PAR, the last element of a tuple goes after the parentheses. It does make a lot of sense in the grand scheme of things. Go read the docs if you want to figure out why. Here, the first element of this pair is OS path, which identifies the file which this event belongs to. And the second element is an anonymous sum type with 4 variants. Here, this specific event that has been emitted is the first variant, which says that the download has been started and its payload, net, a natural number, says the total expected size of the file. Here, 40 bytes. Right after that, a second event arrives, this time saying that 10 bytes have already been downloaded. The either type is just like Rust's enum or Haskell's data, a discriminated union, except anonymous. That's because PAR has a structural type system, and all named types are just aliases. So let's get on with the main function. The next line is fan in. the very famous concurrency pattern. All it does is it accumulates all the events from all the files into a single stream. So far we just have one file, so its purpose might not be so obvious, but wait a bit, we'll have more files. For this single file situation, the fan-in just sucks in the events and emits them back, from where they go into the next line, which is show download progress. This is the last piece of the pipeline. This function consumes the events, tracks the progress for each file, and brings the overall progress report to the console, just like we saw in the demo. Now, what happens when a second file arrives? It's going to be quite a dance. Let's see it in action. A new download file function is instantiated, immediately starts downloading and emitting events. This file is 30 bytes large. At the same time, the first file is still in progress, so it also keeps emitting events. Now we have events from two sources, and this is where the fan-in really comes in. You see, show download progress must process the events in some specified order, but they are coming from multiple independent sources. So fan-in gathers all these events and turns them into a single stream. Watch this. It takes events from both files and emits them one by one. And once the files have finished downloading, the functions end, the final finished events make their way through the pipeline, and that's it! Hooray! So what's going on here? What does this mean? What are these functions returning? There is a lot of concurrency going on here. Where is it coming from? Are these some channels and coroutines? Is this some powerful async await? Or is this a nice syntax for actors? It's neither of those. Look at the code. Do you see the map? Take the hint. It's just lists. But that doesn't make sense. If you're a programmer, you know that this is not what lists do. This is not how lists should work. But ironically, I suspect if you asked a non-programmer, they might be confused why lists couldn't do this. After all, they're just sequences of items. So let's check the types in the code to see how these lists are actually used. Here I have the source code open in VS Code using the par language extension. So I have the syntax highlighting and I can see the types. First thing, yield download requests. It's a function. In par, functions are denoted with square brackets, where the arguments are inside the square brackets and the result type is afterwards. So this is a function that takes a string, which is the URL the server listens on, and a path, which is the folder where the files will be downloaded to. And then it returns a list of these pairs, just like we saw in the visual tour. And so the result of this first line is this list of pairs of the source URL and the destination path. Now, that list gets mapped over this download file function, which takes a pair like that and returns a list of events. I hope you see how that maps to what we saw in the visualization. And so we end up with a list of events, because each of these pairs gets individually transformed into a list of events. And so now we have an individual list of events for each individual download, but for it to be processed by show download progress, we need to turn it into a single list of events. Let's take a look at the type here. Show download progress takes a list of events and the root path and returns the unit type. This exclamation mark, that's the unit type in par, so just like an empty tuple in Rust or Haskell or the null type in TypeScript. And of course, as we already know, that's what the fan-in is for. So fan-in takes a list of events and returns a list of events. In a way, it's just like list flattening, and the combination of map and fan-in is just like a flat map from the type perspective. Except of course, a flat map would put the entire first list in front of the second list and that in front of the third list. And so if we did that, then when observing the download progress, we would always see just one file. Whereas fan-in merges the lists in the order that their items were actually produced. That's why we can observe all of the files being downloaded concurrently. All good, except still, where is the concurrency? Why are these downloads executing concurrently? And what are these lists? Are they even normal lists? Well, let's take a look at their definition. This is how the list type is defined in the standard library. In PAR, you define recursive types using the recursive keyword, where the self refers back to the recursive. The content of the recursive type here is either, which is again the anonymous sum type, a discriminated union with two variants. Let's unpack it. The variants of an either type in PAR always consist of two parts. First is the variant name, here the end and the item, and then each variant has a single payload type. For end, it's the unit type here, so a type with a single possible value. This variant then effectively represents an empty list. And for item, the payload is a pair. A pair in PAR has the first element inside the parentheses and the second element outside of them. This tends to throw people off. So let me say again, this is a pair of A and self. I know this is a very original design choice, but it really does make a lot of sense in the context of PAR, and especially in the context of duality. I recommend checking the docs to understand it better. So this is really just very normal, functional, singly linked list. The equivalent type in other languages would be like this in Rust. I know this is not an idiomatic way to do this in Rust, but I wanted to make a direct translation and also have each variant have a single payload type. This would be the equivalent in TypeScript, where the T field specifies the variant and the P field is the payload. And this would be the equivalent type in Haskell. And so the question still persists. Where is the concurrency? Let's finally answer this question. The answer is concurrent evaluation. Turns out, changing your core execution model has a lot of consequences. We already saw it in lazy functional languages. A list in Haskell is also not the same kind of a list you find in strict languages. Just thanks to the evaluation model, a list in Haskell can be infinite. Well, PAR does not have lazy evaluation, but it has concurrent evaluation. And that gives all the data structures the superpowers needed for structured concurrency. So how does that work? In short, whatever can run concurrently runs concurrently. There are specific rules to that, but that's the general rule of thumb. In almost any programming language, for this code, the argument would evaluate first. Once that happens, the function starts, and once the function returns, the variable is assigned and the code goes to the next line. But PAR says there is no reason for the function to wait for its argument. There may be plenty of things for it to do before it needs to check the value of the argument. And there is no reason for the let to block the rest of the process. And so in PAR, all of these run concurrently. And that explains this map. The download file functions don't block on each other. The second one does not wait for the first one to finish. Instead, they all start and proceed independently and concurrently. The execution model alone makes a normal map function a concurrent map function. The other side of this is that everything is a kind of a promise, a future, whatever you call it in your language. If you have a value of a certain type, it doesn't mean it's there. It means it will be there eventually. However, unlike in other languages where promises can fail or not resolve, PAR's type system guarantees that if a value says it's a string, it will become a string eventually. So everything being a promise does not carry over the uncertainty that comes with concurrency in many other languages. This principle goes deep. Let's take the list. Usually, a list would be stored in memory all at the same time. But in PAR, a list can emerge gradually. Let's take a look. The first item node has appeared, but the value is still not there. Oh, now it arrived. Now the second node has appeared. What's going to happen next? Oh, it's the third node. But the value of the second item has still not resolved. This is perfectly okay. Independent parts of the list can resolve at independent times. Let's see what happens now. The value for the third item has resolved before the value for the second item. Next, a fourth item has already arrived. And now, the end of the list. At this point, a function computing the length of the list would already answer 4. It would not need to wait until the values for the remaining items are resolved. But after a while, the items are indeed resolved and the list is completed. Everything being a promise is the secret behind the fan-in, which can take advantage of this property and merge the lists in the order their items resolve. Actually, you know what? Let's see the fan-in in action in Par's interactive playground. This is Par's interactive playground. It's a feature that makes exploring the language much easier. Here on the left, I have some code. And here on the right, I can run it. And the playground will generate a user interface based on the type of what I run. It's really cool. The fan-in here is a generic function. Unfortunately, the playground cannot run generic functions, but it can run it if I specialize it to some type. So here I have a specialized version of fan-in for lists of strings. So let's compile and run it. All went well. And let's run fan-in string. Now you see, I immediately get a user interface for entering the input to this function, which is the list of strings, and I will also see the output. These buttons here are currently for the outer list, so I can add a list, and now I get buttons for the inner list. I can also add another list, and another list. Now let's see what happens when I add an item to one of the lists. Two things happened. One, I got an interface here to enter the value, but here in the bottom, an item has already appeared. Its value is blank so far, because I have not entered anything here yet. But as soon as I enter something here, the value here resolves as well. And notice, I added an item to the second list here, but the item immediately appeared down here. That's the fan-in in action. Let's add some more items. Now I'm gonna do something else. I'm gonna add an item, and it appeared here. But before filling out the value, I'm gonna add another item somewhere else. Another item appeared down here. I can add another item here, and another one. Now I have 4 unresolved items down here, and I can fill them out in any order. Now I'll postpone filling out this item because I want to show you what happens when I end these lists. I end this list, and another list, and another list. The list down here has not ended yet, and that's because the outer list has not ended. But as soon as I end it now, the output list has ended as well. And that is without this item being resolved yet. However, let me resolve it. Now it's all completed. So that's how the fan-in works. Everything is a promise. We have concurrent evaluation. And nothing needs a wait. Everything gets resolved and synchronized at runtime. This creates a new way of doing structured concurrency, which Par is pioneering. But of course, that's not all that's interesting about Par. What else do we have? Totality. That means no runtime crashes. No deadlocks. Even with all the concurrency, Par rules out deadlocks by construction. And no infinite loops. With the caveat, there is an escape hatch, because not everything is easy or even possible to express, at least with the current totality checker. But it's worth noting that the concurrent downloader demonstrated in this video does not use this escape hatch. And as such, if it compiles, which it does, it's guaranteed to not crash, not deadlock, and not get stuck in an infinite loop. Another thing that's absolutely core to Par, and that's really where it started, is linear types. I could make a whole another video of what linear types bring to the table, but I want to highlight just a couple of things here. One is life cycles in types. What this means is that types become a kind of protocols, which can specify different operations available for a type in different parts of its life cycle. That may sound very abstract, but what it's actually really useful for is this thing popularized in many languages called fluent interfaces, which make heavy use of method chaining to achieve easy-to-use APIs. For Par, this is its second nature. There's nothing more natural than creating and using fluent interfaces. But another very useful thing for program correctness is this notion of no forgotten obligations. Normally, types specify capabilities, but linear types also specify obligations, and your program will be rejected unless you fulfill them. For example, in this concurrent downloader, I would not be able to get a program type checked if I forgot to respond to an HTTP request. The types themselves force me to respond to it, and to respond to it once. And the last thing I want to highlight here is duality from linear logic. It's a big topic, so unfortunately I won't be able to really explain. I recommend reading the docs, which should make it much clearer. But it's a concept very important in PAR, which really enables its concurrency model, and also brings unexpected expressivity. For example, thanks to duality, you get Python-style imperative list generators for free. And there's a lot more. PAR, while very new, is quite a rich language. But before you dive in, I want to mention two things. PAR is different. And that's not just a phrase. It's really one in its family. And that makes the learning curve steep. If you remember learning functional programming for the first time or wrestling with Rust's borrow checker, PAR will be a similar experience. You might feel like you just started learning programming, but it might be worth it. Let me show you what some other people said. I really loved seeing these comments. Here one person said that PAR feels like it came from another planet. And this other person said that it feels like a language from 10 years in the future, and that it's using a wholly different paradigm, which is true. That's because PAR is not a functional or an imperative language in the typical sense. It's actually a process language, something like PyCalculus. Its basis is in this language CP, introduced by Philip Wadler in his wonderful paper called Propositions as Sessions. So PAR is a process language, and I'm not aware of any other practical language based on a process calculus. But the second thing I want to mention before you dive into it is PAR is not production ready. It is very much a work in progress. It definitely does work, as we saw in this video, and it's already pretty capable, but it's still missing a lot of crucial features, such as a module system, an ability to add custom IO bindings, more concurrency mechanism because a lot of things are still not really expressible. The runtime is pretty slow right now, but I'm working on a new one. And there's a lot more to be done. But PAR is very much ready to be explored and has already attracted a bunch of contributors, some of which I now consider my friends. You can install it and play with it, you can read the fairly extensive documentation, and you can come and join our active community on Discord. And if you want to support PAR in a material way, you can sponsor it via GitHub sponsors. I am working on PAR in my free time alongside my full-time job, which is not easy, and any contribution here helps a lot. That's automatic concurrency in PAR. Tell me what you think in the comments, and if you like PAR, feel free to join our community on Discord. Bye bye.